For the example, I'd like to look at a square foundation. So that is, as this content's being established, I'll say it multiple times, that's the limit of our coverage. We have an 18-inch square column. The compressive strength of the concrete is 4,000 PSI or 4 KSI, quite low compared to some that would be available, ultra high strength and so on, but not terribly unusual in that. We have 8 number 8 bars, and that'd be a number 25 if you're looking at the SI system, by the way, of 60 KSI for a yield strength of that steel. The dead load is 225 kips, 225. The live load is 175 kips. So the total load on this foundation is going to be 400 kips from a geotechnical perspective. That's how we would consider that loading scenario. The gamma of the soil above the foundation is going to be assumed to be 100 PCF. That would be the backfill, 100 PCF. I apologize for that getting a little bit light on this copy. And the Q allowable from a bearing capacity analysis, Udrona, Terzaghi, or Vasek, or whatever is decided as appropriate, is 5,000 PSF for this problem. And we have a depth of footing 5 feet below the ground surface in this case. The footing itself is 4 KSI and 60 KSI steel. So it's matching the column in this case, by the way, but still at generally lower end of those, at least the concrete strength. So I'd like to look at the geometry of the footing just a bit. It's buried like this, and you folks are old pros at this stuff, so no need to go through too much on this. And I'll make some assumptions here and, get through this next step kind of quickly, which would be the net bearing pressure available being the 5,000 minus what I'm calling 625. And I'm assuming a gamma average in this case of concrete and backfill to be 125 PCF for this case. And that's a little bit of a loose assumption. You can certainly refine this, and for proper design, problems and full on when you're doing both the geotech and the structures, you would be able at the end of the problem, get in and, refine your dimensions for how thick this is and so on. At the moment, we really don't know how thick that is because we haven't designed it yet, the concrete. So I'm just saying material in this region, meaning from the ground surface down to here, it's about 125. And that means the concrete is about 150. That's a very typical assumption for concrete, and that number generally would include some reinforcing steel kind of built in, averaged out throughout that zone. And we have this soil above, which is going to be, around the 100 value, a little bit lighter on compression or compaction than what you might find with larger compaction, because this is going to be done by hand. You have a little hand compactor or something in the region right around these columns, a little more delicate compaction work. And that means that we have the 5,000 is what this foundation can hold according to Vasek analysis, for instance. But it's got 625 coming in of material here that's already acting on the base. That's just the dead weight of all the stuff that's there, the geo stuff, the footing and the backfill is part of that 5,000, by the way. So this brings us to 4375 for a value. And this highlights that distinction of a gross capacity versus a net capacity, by the way. So the required area is going to be the 400 kips divided by this 4375 PSF or 4.375 KSF going into kips land for a structures problem and using more of that terminology. What we end up with there is 90.3 square feet of footing is needed, and with a square shape, we can establish that that would be a 9-foot 6-inch foundation kicking up to the next construction size. And this is unfactored loads for the bearing capacity analysis. So note that for the geotech, portion of work, you stay with just 400 kips. That's it. We're not getting into factoring stuff and so on. And I'm doing some arm waving here of just pulling this out of a hat and so on. I'm not doing a full-on analysis. You guys have proven very well that you know how to do those sorts of analyses already. So for strength design, and when we get around to structural design, that is, the upward stress acting on the base of the footing is what we're going to be designing. And that means we have to take the dead load, live load, and inflate them for those factors. And we will have 1.2 times the 225 times the dead load, and 1.6 times that live load. And now all of a sudden we have 550 kips that we're designing for as an ultimate load. And the Q, again, this reaction stress acting upward on the base of that footing, is going to be load over area. And that will be 6.1 KSF, kips per square foot, or 42.1 PSI. And you're going to see throughout this exercise, throughout this example, that there'll be some unit conversion changes and so on. And I want you to keep an eye on those, as they can be, they are important and can be critical in how you approach a given component of the problem and what, it might relate to what table or what portion of a table you are using. So at this stage, we're ready to design the for shear, which will be the shear analysis of the concrete. And what we're trying to design here is the thickness of the concrete. So that D parameter I spoke of earlier, the thickness of the pad. And I will first run through here rather quickly, just this little content here that's on the screen, the version for one-way shear. And you won't need to do this. You won't even need to, perform these calcs, but I'm just showing it so you have some understanding of it. And you'll find out when we do two-way shear that indeed that one controls, as it always will for square. For, say, the design project, I'm fine with you just saying square foundation, two-way shear controls, and only show that analysis would be fine. So we have V sub U, the shear, the ultimate shear being addressed here. We have 114 inches, that's the 9 feet 6 inches. We have a D dimension away from the column. We don't know what that is yet. And what is that going to be? That's going to be 48 minus D. And where did that come from? 57 minus D minus 9 is where that's coming from. And the 9 is half of the column dimension, by the way. It's an 18-inch column. So we're slicing the column in half, slicing the footing in half. There's the 9-inch, there's the D, and that leaves this remainder. So VU is going to be the 114 times the 48 minus D times the 42.4 PSI. So remember that this is our stress that would be acting, so far in the class, we've been talking about it as a stress acting downward inside the footing, acting on the soil. But what do you know? Every action has a reaction. So it's also the soil acting right back at that concrete. And now we're designing the concrete. And what is being designed here, that area 114 times 48 minus D is this shaded region here. So that region is our critical section for one-way shear. So we're considering what is the upward stress acting on that chunk of foundation and establishing that it would be the value of Q that we've been calling so far. So what we have on that is this equation here, just, expand it out is all that is. And then we have a V sub C. And I think I define these better in the next section here. I believe, I do define VU and VC in the two-way shear where it's kind of the takeaway for this exercise. So hang tight on the meaning of these, and you'll see that in that next example. So VC is going to be 2 times the square root of FC prime times B times D, where B is the width, and that's 114 for our case. So 2 times the square root of compressive strength of concrete in PSI. Mind you, this is, developed, this equation is developed for PSI. This doesn't work for, you can't just pop in any numbers here. It works for PSI, and that's going to be a little bit of a hiccup for you in the design project when you have to do a metric foundation or an SI units foundation. The way that I'll have you handle that is simply convert over to English units temporarily, buzz through this section, figure out what your depth is, convert it back to metric, and you'll be off to the races. And if you are a structures person and have all the equations for SI in this regard, charge on and use those. I'll invite that, but not require. And again, I'm not trying to derail this course and have it become a structures class. So this is 14,420 times D if we expand that out. And we know that VU must be less than 0.75 VC. And that is equal to 1018 times D, which we had from above. So if we set those two equal right here, and that line is showing that, you end up with this equation, we solve for D, and we figure out a D of that footing to be 14.8 inches for construction purposes. You would kick that up to the next inch, 15 inch. And I hope seeing the definitions of these various terms with VU and VC will help with understanding this on the two-way shear, and we'll see where that compares to this 15 inch. So for a two-way shear, by the way, it always controls for square. In PSI, we know that we have 42.4 PSI. We established that earlier. And for the V sub U, which by the way is a required strength at the factored loads. In other words, the shear force acting on the perimeter, calculated as total upward pressure minus that within the perimeter. And what I'm speaking of here is this dashed line, that being the perimeter of this shear zone, that cookie cutter that's cutting through the footing pad that is replacing the real geometry of a pyramid type shape. And this geometry we have seen in the graphics that were presented in those slides. So you have those, kind of proper graphics version of that. D over 2 is the distance out to that perimeter from the column edge to that cookie cutter. You progress out D over 2, and you do that going both ways. So the whole dimension of the cookie cutter, I'll use that term rather casually, but I hope that it means, that you understand what I'm speaking of there clearly. It will be 18 plus D, and that would be going on in both directions. So we have for V sub U, this parameter of the required strength at these factored loads is going to be 114 inches squared minus 18 plus D, that quantity squared, times 42.4. And we're in PSI when we look at that number, PSI. So what we have here is this shaded area, which is everything outside of that dashed perimeter, acting upward. And the column load inside that perimeter acting downward. And we're trying to establish the shear of concrete that will be required in that zone. And therefore, we can figure out the dimension of the concrete in terms of the thickness of that pad of foundation. And this is simply expanding this equation out, all of that stuff, to get to an expression for V sub U, which ends up being some rather large numbers, but is just a straightforward expansion of this equation, which I think is somewhat intuitive, or at least can be seen in the diagram as being that upward load outside the perimeter. Along with this.
Yes, sir.
Yes, Eileen. What's going on?
Is D the width, like the thickness of the footing?
It is, absolutely. D is the thickness of the footing, and we'll refine that definition a little bit when we get around to the details of where the steel is and how far does D go down. But you can think of it for now as just, it's the thickness of the footing.
Okay, thank you.
It will not include that bottom cover material, that bottom 3 inches. And as it turns out, it's not going to include some of the steel dimensions on the bottom. But we'll refine that as we go. But for now, you can just think of it as the D, the depth of footing, the thickness of that pad. The V sub C, on the other hand, is the nominal punching shear strength on this perimeter. So now we're on the strength side. And if we look at the punching, or for two-way shear, the equation for VC is going to look like this, where it will be 4 times the square root of FC prime, again in PSI, times B naught times D. And B naught is defined as the perimeter length. And you see that defined down here with a little bracket, 18 plus D. That's one side of that dashed perimeter in that figure, times 4. So it's the length of that perimeter times the height of that cookie cutter pattern, let's call it, the thickness of the pad, in other words, times the square root of FC prime times 4, just a constant out front. And what we'll do here is expand this to be V sub C. And shear gets a factor phi, a reduction factor of 0.75 as it turns out. That would be the reduction for shear mode of loading and shear mode of resistance. And we're going to factor the nominal strength to a design strength using this phi of 0.75. So this now is going to be a design strength. And VU will be phi times VC. So you see where we're heading here. We calculated a VC. We're going to multiply that by 0.75. And up here, we calculated independently a VU based on loading. And what's going to happen is we're going to set those two equal to each other. And then that allows for solving for a depth of footing. So we have a V sub U in this case. Which is the expanded version of that expression above. And again, getting into some big numbers, but that doesn't matter. You know, the calculator can handle that just as easily as the little ones. And we will set those two equal to one another because we know that VU and VU must be the same. And that allows us to have an expression, quadratic expression, and good time to have your, oh, sorry about that. Good time to have your calculator up to speed for solving quadratic expressions. And a very simple, item to be able to just pop in the ABC parameters and get the roots for that. And the roots on this are going to come out to negative 37.1 for a thickness. Well, that doesn't make any kind of practical sense. Or 18.1. And that certainly sounds reasonable. By the way, 18.1 is greater than what we had up here, 14.8. So it demonstrates now mathematically that the two-way shear does indeed control. And again, for purposes of square foundations, you can know that going in, that two-way controls, and I'll say cut the corner and make your calculations reasonably easy in that regard. Questions on that flexure, or shear analysis, excuse me, the shear analysis for thickness of the footing. Cool. My expectation again is that you'd be able to jump in here and just do this with different column loads and steel and concrete strengths and so on and run with it. Next up, we're going to determine the area of steel, and we do that for a flexure analysis. So this is the cantilever, critical cantilever section, if you recall. And we have a similar type equation here in which mu is going to equal phi mn in this case. And that will be 0.9 times area of steel times yield stress of that steel times d, depth of footing, minus a over 2, where a is that Whitney stress block height that we spoke of in the cartoons from the textbook that showed that quite nicely. And little a is going to be defined as this, and that is defined as the Whitney stress block size, and they're deriving that and so on is beyond what I want to get into here. We can just take that at face value and say that this shape with what's highlighted here in blue is actually equivalent to the actual stress distribution, which is parabolic in nature, leading down to a zero value at that neutral axis, where you have a crossover from compression in the section at the top towards tension in the section at the bottom. And what we will do with that Whitney stress block is identify its centroid and say that the resultant of the compressive forces actually acts there. And we will find the centroid of the steel. That's pretty easy, right at the middle of the diameters. And that would be the location of the tension resultant. And therefore, D minus A over 2 is going to be that dimension between them. We know going in, kind of like thickness of foundation has to be positive, that D minus A over 2 must be positive. We know that as well. The tension here, the resultant tension force, is going to be area of steel times the stress in the steel. So the M sub U in this case is bringing us back to statics, where you have a QU L squared over 2. And that should remind you a little bit about statics, with a cantilever beam being loaded with a constant distributed load across the top. And that's what's going on. We have a reaction load down here of soil acting on the footing. And the critical section here is going to be right up against the column. And that's the worst case location for that. And this end of the footing will be wanting to bend upward in that case from a structure standpoint. And we're resisting that. And we do know the L value. So L is going to be 9.5 feet, 9.5 feet, 9 feet 6 inches, times 12 minus 18 over 2. And that's 48 inches. So L in this case is 48 inches. And this M sub U is the bending moment on the critical section. So putting in our numbers, QU is good old 42.4 PSI. That's the soil stress acting on the foundation. 48 inches, that L value squared over 2. And we come up with 48,800 inch-pounds per inch of footing, if we think of it like that. Or we have 5 million and change inch-pounds for the entire footing. And you can do this either way. It doesn't matter which you design in, but you need to know which you're designing for, because we're going to be selecting steel from this, and you need to know whether you have to multiply that at the end by the number of inches in the foundation, or if that's the whole amount for the entire footing all in one shot. That has to be distributed throughout the footing. So at this stage, we have phi mn will be 0.9 times area of steel times yield stress of steel, 60,000, times this 19, that's our D if you recall. When we came out to 18.1, we elevate it to the next inch for safety and construction purposes. And that would be minus AS, area of steel, times 60 KSI, over 0.85. This is getting into that Whitney stress block stuff. 4 KSI, 114 inches, times 2. We can expand that to be phi mm is this value. And we know from the onset of this section that phi mn must equal mu, so we can then set that to this value for the entire footing. In this case is how this is laid out, because we're doing it for 114 inches. Expand that out, or rearrange the equation actually to get a quadratic, and we end up with 2 AS values, 2 possible solutions here for steel required for that entire footing. It's either 239.9 square inches or 5.55 square inches. And what we do at this stage to figure out which one of those is the correct solution is to assess that Whitney stress block dimension A. And that is equal to AS times Fy over 0.85 FC prime B. Again, that's that Whitney stress block definition. And we start with the 5.55 and come up with 0.85 inches, a real small zone on top of compression. If we move to the 239.9, everything else in the equation remains the same. We end up with 37.1, and that would make the neutral axis outside of the footing, so that's not going to work. We have a compression zone and a tension zone, if you recall, in that foundation, organized somehow and fitting in there somehow. And this tells us it must be this smaller version with a rather small compression zone in this case, allowing for that neutral zone to actually exist within the foundation. We have some minimum reinforcing as well. An AS minimum is going to be tabulated in table A4. And I'd like to run over that table for just a minute. I'll let you get some of this jotted down. And you see that there's 2 versions here. AS min equals this first equation, and that has to be greater or equal to this second equation. So we actually have to check both of those. And the first one, putting numbers into those equations, will be 3 times square root of compressive strength of concrete in PSI over yield strength of steel, also in PSI, times 114, our dimension, considering it's the end of the page, the entire length of that pad, if you will, that footing pad, times 19 the depth of that footing. And that gives us 6.84 square inches. And that must be, that value, which we just determined, must be greater than this second equation, which we can pop in here, 200 times 114 times 19 over 60,000. And that comes out to 7.22. And that controls because it's larger than 6.84, by the way. So 7.22 controls. And what do you know, with structures, we have to check one more thing and see that we are indeed below a maximum steel ratio. And a maximum steel ratio is established to ensure that you have, again, a ductile failure. You want that to be a ductile type failure, and you can have too much steel in a design, and that you have to ensure that you actually don't get too much steel. So there are limits on how much steel can go into a structure. And I'll bounce over to the tables now and take a look at that table A4 for just a moment. So here's table A4, and we have, first off, row min for 200. Row max, here we go, row max, and that is going to be for the 60,000 PSI steel and 4,000 PSI concrete. And our row, and our row min on this and the row max on this is 0.0033, and that ends up being considerably less than a row max identified here in the table. So that's just a quick check that you do on the tension controlled members, that you're not putting too much steel into a structure to ensure proper behavior of that structure overall. And on kind of safe failure mode is where that's really ensuring what you have. And if we go back to this, that means that we are searching now for 7.22 square inches of steel for that entire footing is what this means. And I'd like to go back to our table at this stage, our design packet. And assess groups of standard bars, dig in here and try to find where is 7.22. I mean, of course, there'd be numerous options that may work, and we simply need to be above that number is all. You don't need to be too much above, but you certainly need to hit that as a minimum. And does anyone see a reasonable value here that would be somewhat above the value of 7.22 square inches. Six number 10s. All right, that's going to get you a 7.62. Okay. That sounds fine, Karamjot. Thank you. So that would be an option for you to run with on that kind of problem. And again, there'd be multiple answers that may work for you that are going to fit the bill and so on in this regard. And I'd like to get back here. And I had established 12 number 7 bars in each direction. That means, you know, this is a crisscross pattern. You have to go both ways on the foundation in that case. And I had this providing 7.20, so sneaking just below it. I think Karamjot's version is, you know, prudent to actually come in above, but when you're that close, you know, 2/100ths of a square inch off, I think that would fly as well. So it's just a matter of selecting the appropriate combination. And something to consider here, a practical consideration, would be matching the column steel. And we know that we have number 8 bars being used for the column, and that would just keep an efficient and simple construction site for operations in that regard. So it's not required. This certainly works, but there is value in keeping things simple for contractors. It leads to higher quality workmanship just in avoiding potential misplaced bars or confusion on jotting notes down and which are going where and so on. You know, little things can happen and go wrong, and the more simple you have it, the more foolproof this would be. So I think I'm going to cut our work on this example here, and we'll be able to wrap this up pretty quickly next time. I don't see any issue with finishing it and having plenty of time for you know, some group work on the final project on Wednesday. So you can plan on that and plan to be meeting in breakout rooms with your partners on that final project for a good chunk of the session. I would think half the session or more. And one note, I do have the deadline for homework number 5 set for tomorrow afternoon. I think it's 2 p.m. or something. How does that sound? How's that working out for people? Good stuff. We're getting there. I'll say that I'm negotiable. You know, but I am strongly encouraging you just knock it out, get it done. It's a catalyst. Having a deadline just gets the darn thing off the table and gets it done. So the one note on that is if on a case specific basis, if you're really in a pinch, let me know and I can work with you on a short extension to that without any issue. Another item, the midterms have been graded. I'll add to that finally, and I apologize for the